All right, so here we go with the lecture for this week for Chapter 4, which is dealing with geologic time. Now, to preface this, geologic time, as I've stated before, is kind of hard for people to grasp simply because we are talking about a very, very large number and a very large amount of time. We're talking billions of years, where the average human lifespan is only 100 years at best. And just like I said before, the time I spend droning on in class lecturing for 2.5, 3 hours can seem like an eternity. With that said, let's go ahead and get started. Again, we're covering Chapter 4 in the book, so hopefully you've read ahead. If you have questions, I'll gladly be answering those next Monday. So we're going to start out with 1869 and an explorer by the name of John Wesley Powell, who, if you remember your Arizona history, might recognize the name as the gentleman who was the first person to successfully raft through the Grand Canyon. Regarding his trip in the Grand Canyon, Powell is quoted as having stated, "All about me are interesting geologic records. The book is open and I read as I run." This basically is what we talk about in geology in reading the rocks. The rocks tell us a story. Now, when we're dealing with time, geologic time, there are two types of time. There is relative time, and relative time is just simply putting things into their proper order. So this came first, this came second, this was third. Again, the analogy for this is if I take a bunch of pictures of somebody making a pizza or putting a car engine together, you should be able to basically, based on the evidence of the photos without any other knowledge, be able to roughly put everything into the proper order. Absolute dating, on the other hand, is a specific date or a specific amount of time that has occurred since the rock unit or the geologic event occurred. Now, this is a newer concept and something that only has been around now for not even 100 years yet. So we'll talk about that more later. Now, to begin with, how old is the Earth has been a very basic fundamental question. It's been asked for a couple of thousand years at least, if not more. Now, there was a gentleman by the name of James Ussher. He was the Archbishop in England. He lived from 1581 to 1665, and he determined that the Earth was created. Now, ready for this, because you got a month and a half to get ready. On Sunday, October 23rd, in the year 4004 BC. And he did this based on biblical genealogy. So he looked at how old somebody was supposed to have lived, how old their children were supposed to have lived, and so forth and so on, and he worked out this. Now, for nearly a century, the thinking that the Earth was older was actually heresy. It was a crime punishable by excommunication from the church, torture, or even death. Now, George Louis de Buffon, who lived from 1707 to 1788, assumed that the Earth cooled from a molten state. And so he estimated, based on the size of the Earth and how long it would take for the Earth to cool to its current temperature from a molten state based on molten iron, that the Earth was more or less about 75,000 years old. Other scholars used deposition rates, looking at how much sediment was deposited, how thick the sediments were, and then looking at how thick sedimentary rocks were, and they estimated the Earth was anywhere from about 1 million years old to about 2 billion years old. John Joly, who lived in the 1800s, estimated the age of the Earth to be about 90 million years old based on the salinity of the oceans. Now, he didn't account for the fact that salt deposits remove salt from the ocean, and so he didn't calculate properly this recycling, so he came up with a pretty bad answer. Based on meteorite data, though, we now know that the Earth is approximately 4.6 billion years old. That's when the solar system at least began to condense. We know this universe, based on all the measurements we can take right now, is about 13.3 billion years old. Come into the picture is James Hutton. He lived from 1726 to 1797, and he is basically considered the founder or the father of modern geology. He's famous for one primary principle, the principle of uniformitarianism. This is the idea that the present is the key to the past, and the past is the key to the future. The idea that basically, unless something radically changes in the system of the Earth, the processes that we see operating today were the same processes that operated in the past, and they will be the same processes that will operate in the future. It is said that he came up with this based on a picnic. He was sitting on a shoreline, sitting on some rocks, and he noted that in this upturned strata of this sandstone he was sitting on were structures that were just like the structures in the sediments on the beach below him. And he realized that given enough time, though the process he could see in front of him on the beach would create the rocks he was on. Now, in the 1830s, a gentleman by the name of Charles Lyell published a book called Principles of Geology, where he championed Hutton's ideas. Now, in 1866, a gentleman by the name of Lord Kelvin, whose name might sound familiar for those of you that have had other science, he came up with the Kelvin scale of temperature. He wrote a paper along the lines of the work of John Joly and argued that the Earth was actually cooling and could be no younger than 20 million years and no older than 400 million years, sorry, not 40, 400, based on the cooling rate. He campaigned for this younger age for about 40 years until the discovery of radioactivity at the end of the 19th century. And then the realization in 1905 that it could be used to date rocks. Now, let's look at how we come up with relative dating before we start getting into the issues with absolute dating. Now, there are some principles that we have to keep in mind with this, and I'm going to try to draw these out because the visuals can help with this. The first is the idea of superposition. And what superposition basically says is that in an undisturbed sequence, the oldest material is on the bottom, the youngest material is on the top. Think about a child's backpack during the course of the school year, or if you've got a teenager at home, or we're a teenager that had a rather messy room, the fact that the oldest stuff is going to be on the bottom level of the floor and the younger stuff is going to be on top of that. Or a pizza. The oldest part of the pizza, when you're making the pizza, is the crust, and then everything else goes on, if you're looking at just the order of everything going on. Another one is the idea of original horizontality. Original horizontality basically states that sedimentary particles in water and under gravity are deposited in essentially horizontal layers. This is why if you look at a house that hasn't been cleaned in a while, the horizontal surfaces have a thick coat of dust on them, while the vertical surfaces have very little dust on them. And then there's the idea of lateral continuity. This basically is the idea that sediment is going to extend laterally until it either thins out and pinches out, meaning that there's no more of that sediment being deposited, or it ends up at the edge of whatever it's being deposited in, if it's like the edge of a basin. Okay, now those three works were the ideas of a gentleman by the name of Nicholas Steno, who lived from 1638 to 1686. James Hutton did give us one other idea from his period of time, and that was the idea of cross-cutting relationships. Basically, what cross-cutting relationships is the idea of is, imagine I have a stack of layers, okay? And let's now imagine that something comes and cuts through those layers, like so. Whatever cuts is older than what is cutting. So this section here in red is actually older than the layers it's cutting through. So basically, you cannot cut something that doesn't exist. So whatever is cut is older than what is cutting it. Another idea is the idea of inclusions. Basically, inclusions are if I have a layer of rock and I've got chunks of other rock in it, sort of like a conglomerate, which we haven't talked about yet, but here I have these chunks here. Whatever is included in a layer of rock is older than the layer of rock. So, best example I can come up with this is a chocolate chip cookie. When you make a chocolate chip cookie, technically speaking, the chocolate chips existed before the rest of the cookie. You had to make the batter or the dough for the cookie, and then you had to incorporate the chips into that, and then you had to lay it out. So technically the chips are actually the oldest part of it. Well, we also have the idea of fossil succession, sometimes referred to as floral and faunal fossil succession, or just floral and faunal succession. This is basically the idea that fossil life forms or assemblages, which are groups of fossils, succeed one another through time in a regular and determinable manner. It also shows that certain fossils, we can see the progression of evolution through the different species over time. Now, floral and faunal succession helps us see that time is happening, but more importantly, it will also lead us to being able to do what we call correlations. If we see certain fossil assemblages in a specific rock in a certain area, and we find the same fossil assemblages in a different area, maybe a different rock, but same fossil assemblages, we know that it was roughly deposited in the same time frame, even if it wasn't in the same sedimentary environment. Then we have the unconformities. And now, unconformities are hard for some people to understand, but they're a very simple concept. All an unconformity is missing time. That's it. It's just missing time. All it means is that for some reason or another, either a piece of the rock record didn't get deposited, or it was eroded away and is missing. So it's just not there. Now, there are three types of unconformities. The first of these is the angular unconformity, where you have younger horizontally laid rocks under tilted older angular rocks. And basically, since we know that original horizontality says that those rocks should have been laid down horizontally to begin with, we know that something had to happen between them being laid down horizontally. They had to be tilted up, they had to be eroded down, and then you get new deposition on top. So that is angular unconformities. Next up is a disconformity. Now, disconformities can be a little harder to note in the field unless you know what you're looking for. So I'll give you an example of what we might be looking for disconformity. And you can actually see this, one of these examples, if you're driving up I-19 to Green Valley or Tucson. So basically, on one side, I'm going to see if I can do this where I can just do this the way I'd like to. On this side, I got a bunch of horizontal layers, and yeah, I can't tell if there's a disconformity in there or not just by looking at them. But if I look at the fossil assemblages, I look at the materials, maybe even look at the surface, I have a case where either what happened is at one point between this bottom layer here and this next layer here, sedimentation just stopped, or there was erosion and it was eroded perfectly flat and then new deposition occurred. Kind of hard to see it in a situation where all the layers are perfectly parallel. Generally speaking, you need a fossil assemblage of some sort to be able to spot it, or evidence of erosion on the surface, which might include inclusions of the bottom material in the next layer up. The other version of it, though, is where you have a paleo surface. So you have a paleo landscape surface, and that surface has now been buried. Well, you only get a landscape surface if there was erosion. So imagine the hills and valleys around us, and then suddenly this massive influx of sediment fills everything in and flattens it out. Well, that would be an example of a disconformity. So it's basically horizontal layers that are separated by an erosional surface or a halt in deposition. Lastly, there is the concept of a nonconformity. A nonconformity is a type of unconformity where what you have is, and I'm going to draw this with a horizontal surface, but the surface doesn't have to be horizontal, and I'm going to just kind of draw it with two different sides. It's going to happen when you have rocks of different types. Namely, I'm going to have older igneous or metamorphic rocks, and they are going to be overlain by younger sedimentary rocks. That's all it is for a nonconformity. So a nonconformity is basically just older igneous and metamorphic rocks. Generally speaking, they're old enough and they're the type that we know they had to have occurred at great depth. It took great pressure and a great depth for the igneous rocks, and usually great pressure and heat for the metamorphic rocks to be formed. And then something's happened, they've been brought to the surface, they've been worn down, and then younger sediments are deposited on it. So we know that we have a great interval of missing time. If you use all of those ideas, you basically can figure out by looking at a rock system or a crosscut what the sequence was. For example, I'll just draw something out here. And let's see, let's just do this, and I'm going to now, one of the things that we do sometimes in geology is we use certain symbols to show certain types of rock. So what I've drawn out here is a simple system. It basically has two symbols on it for the rocks, bunches of dashes and then a bunch of dots. The dots usually represent sandstone, the dashes usually represent shale, something like this. So looking at this, I can start to figure out what happened here. I pretty much know that this layer here at the bottom is going to be the oldest because of superposition, followed up by this layer of sandstone, this layer of shale, this layer of sandstone. Now, what we'll talk about when we get into talking about sedimentary environments and whatnot, basically this is telling me that sea level in this particular area is going up and down. It's up here, down when we get to the sand, up when we get to the shale, down when we get to the sand, and then up again for the shale. But there's a break right here. This is a disconformity at this boundary here because we see that we have a fault right here. And this fault, as you might know if you recognize it from physical geology, is a reverse fault, meaning that the head wall moved up, the foot wall moved down. So we would expect there to be some material that's up above here that represents the same level. It's gone, it's been worn away, and it's been worn pretty much flat, so now we have this other shale layer that's on top of it. So we just start to put things together. And that's just using the basic principles. We know that by cross-cutting relationships, the fault had to happen after this layer, but before this layer. So we can do this with these things and take relatively complex diagrams of the actual geology of the Earth and figure out the basic order of occurrences. Now, absolute dating, on the other hand, is a little different. We have to remember some things about atoms first and foremost. Remember that the number of protons is what determines the type of element it is, and it also determines the atomic number of an atom. The number of protons plus the number of neutrons are basically going to be the atomic mass of the atom. Different atomic masses with the same atomic number means that we're dealing with different isotopes of the same element. And basically those isotopes are what are going to end up either deciding what's stable or what's unstable. So radioactive decay is basically the spontaneous transformation of an atom into an element through the emission of energy in subatomic particles, i.e., it's basically what the alchemists were looking for in trying to change materials from one element to another, although it happens through a different process. Now, there are three types of radioactive decay that we have to be worried about or concerned about for this case. One is what we call alpha particles, or alpha emission. An alpha particle basically is the following. You have an alpha particle, which is generally made up of 4 subatomic particles, and those subatomic particles are 2 protons and 2 neutrons. So something like this. So we have 2 protons and 2 neutrons. Basically what this is going to do is the atomic mass number of the element is going to, that emits an alpha particle, is going to drop by 4, but the atomic number is going to drop by 2. Okay? Beta decay, on the other hand, is where an electron is fired off from a neutron within the nucleus. Okay? Basically, long and short of it is, if you take an electron and merge it with a proton, you create a neutron. So if a neutron decays, it will fire off an electron, and you're left with a proton. So the result of that is the atomic number will increase by 1, but there is no change in the atomic mass number. And then finally, you can have something that's not really a form of radioactive decay, but it does have a significant change on the nature of the element and the nature of the nucleus, and that's electron capture. This is basically when an electron bonds with a proton, changing it into a neutron. Generally speaking, this usually happens for certain elements when a high-energy electron, i.e. a cosmic ray, comes in from outer space and slams into the nucleus. What this has the effect of doing is dropping the atomic number down by 1 and not changing the atomic mass at all. Now, some radioactive decay sequences take one step. They go from the parent straight to the daughter. Others take multiple steps, where they go from a parent to daughter 1, daughter 2, daughter 3, daughter 4, until they get to daughter final. But what we really are concerned with in radioactive decay and absolute dating is the time it takes to go from the parent material to the final daughter product. And this is what we call the half-life. This is the time it takes for half of that material, that unstable parent material, to turn into the stable daughter element. It can range anywhere from a billionth of a second to about 49 billion years for the materials we have. But it's always the same amount of time for the same isotope of the element. It's always 50%. So the first half-life, it's 50%. So we go from 100% to 50-50. The second half-life, it's 50%. So we go from 50-50 to 75-25, or 25-75. Another half-life, we go to 12.5 to 87.5, so forth and so on. The ratio goes from 0 to 1, infinite, and then after the first half-life, it's 1 to 1. Second half-life, it's 1 to 3. Third half-life, it's 1 to 7. If you look at it mathematically, there's a pattern of it's going to be 1 to 2 to the nth term quantity minus 1. So 2 to the second power is 4. So if I subtract 1 from that, I get 3, because 1 is on the other side. Now, when it comes to working with radioactive decay and trying to do an absolute date for something, one of the things that we have to do is we have to be very, very, very certain about minimizing uncertainty. We want to use a material that's not weathered. We want to use a material that was not metamorphosed, because if we use something that's been metamorphosed, then we're looking at potentially the date when it reached a certain temperature, not when the material formed. So we need to look at material that's been essentially a closed system so that we don't have any contamination. Unfortunately, dating fragments in a sedimentary rock means that we're actually dating the age of that fragment, not the sedimentary rock in general. So basically, what we end up with is about the only thing we can really date well radiometrically is igneous rocks. So we have to use igneous rocks as our markers. So we have to look at the type of igneous rock and put it into context. If it's an igneous rock that formed below ground as a plutonic one, we really cannot use it too much to date the materials around it, except that we know that it had to be younger than those materials, so that we can give an upper age date on those materials. But extrusive igneous rocks are fantastic because they can form thin layers in a sedimentary sequence and give us very, very specific time intervals within that sequence. Now, there are several long-lived radioactive isotopes that we can use for dating. For example, uranium-238, which turns into lead-206, and that has a half-life of 4.5 billion years. Uranium-237, which turns into lead-207, which has a half-life of about 704 million years. We have thorium-232, which turns into lead-238. That has a half-life of about 14 billion years. Rubidium-87 will turn into strontium-87. That has a half-life of about 48.8 billion years, almost 49 billion years. Potassium-40 will transform into argon-40, and it has a half-life of 1.3 billion years. And there are other pairs that we can use that they're mentioned in the text, but those are the most common ones for most geologic purposes. Now, there is one other one. I'm going to mention it in just a minute. But there are a couple of other processes that we can do. First of these is fission tracks. These are great for dating samples anywhere between 40,000 to 1.5 million years old, and it's caused based on the damage caused by the decay of uranium. When uranium decays naturally, one of the byproducts of that decay is it throws a neutron out. When it undergoes a fission decay, where it splits into two pieces, instead of normal decay where it shoots out an alpha particle, unstable breaks into two. It shoots a neutron out. It actually shoots two neutrons out. That's one of the reasons why you get a cascade effect for nuclear bombs or nuclear energy. That neutron firing through a crystal can actually damage the crystal and leave a track that we can actually then look for and count. And so we can actually, based on the number of fission tracks within a sample, get a rough idea for its date between 40,000 to 1.5 million years old. Another one that we can do ahead of time, before we get to the last one I want to talk about for method, is tree rings. Now, tree rings are only good for the last few thousand years, generally speaking, but it's a very powerful one because within a given area, trees are going to grow pretty similarly. Now, when you look at a tree, if you cut it open, if you look at wood, what you'll see is a set of rings. Basically, you have a light ring followed by a dark ring. And it turns out that from here to here, this area right here, including the dark ring and all the way almost to the dark ring on the other one, that's 1 year's worth of growth in a tree. The light part is what is laid down during the growing season when the tree is actively growing, so the spring, summer, into the fall, maybe into the fall. And the dark layers was laid down in the late fall and in the winter. So the tree is still growing, but it's not growing anywhere near as fast. It turns out that you can correlate these rings from different trees of different ages and build up a record for an area. And we've done this in many parts of the world going back up to about 14,000 years. So you can actually look at tree rings from a piece of wood and go to the record and actually correlate that to the record of tree rings for an area and actually figure out when that tree lived. Now, another way to do it if you have wood is radiocarbon dating. Carbon-14 is a radioactive element that is in the atmosphere. It's in your body. You are radioactive. There is a certain percentage of the carbon in your body that is carbon-14. And as long as you are alive, that amount stays constant. What happens is cosmic rays, i.e. high-energy electrons, slamming into the upper atmosphere, convert nitrogen-14 into carbon-14. Now, carbon-14 has a half-life of about 5,730 years. So that means that we can use it to date anything up to around about 50 to 60,000 years old. So it's great for looking at human occupation or recent animal finds in caves, mummifications in caves. So we can do that. Now again, we have to be careful about contamination. Any other source of carbon, i.e. hair, skin samples that come off of the tester, can contaminate the sample. Now, if we look at geologic time, one of the things it tells us, and this is the no-duh of geologic time. I'm a geologist by training. You tell me that the climate of the Earth is changing, my answer, no duh. The geologic record tells me this. If we examine the Earth's history, it shows us the climate. And it shows us that the climate has and continues to change since the day the Earth was formed. There have been periods where it's been much, much warmer than it is today. It is the truthful statement to say that the Earth is warmer today than it has been in the last 120,000 years. That is an absolute truth. It's also truthful to say that 134,000 years ago, the Earth was approximately 4.1 degrees centigrade, or around 8.5 degrees Fahrenheit, hotter than it is today. And if we go back about 30 million years, it was even hotter than that. So we know that the Earth has been much hotter. We also know it's been much, much colder. There are at least 2 periods in Earth's history where the geology suggests that the Earth was frozen all the way down to the equator. There were the ice caps went not just at the poles, but it was ice all the way around the Earth. This is called the snowball Earth hypothesis. At least once about 2.5 billion years ago, and once about 600 million years ago this happened, apparently. So we know from geologic history the Earth's climate does in fact change. In fact, it's a dynamic system. What we don't understand is how much of an impact we really do have. We know from a local standpoint we can have a great impact. From a global standpoint, it's looking like we can have a severe impact to a strong impact, but there's a lot of things about the Earth's climate that we don't know, but we keep learning more about it by reading the rocks. So that's it for Chapter 4. I will post up, hopefully tomorrow, the lab for Chapter 4. I can't remember the number off the top of my head, but I'll get it up. The lab assignment for that. I will see you guys on September 10th. Have a good one.